require.
Okay. Okay. Yeah, so this is our divide and conquer recitation. Yeah, if you have any like questions or if you have trouble like hearing us or if you can't see the screen, like please feel free to like unmute and say something. And also if you're saying something and it feels like we can't hear you, then put it in the chat because that means there's some like technical issue. But yeah, hopefully like if someone speaks up, we'll be able to hear. Yeah, so yeah, what we want to like do for this recitation is basically just kind of go over what divide and conquer algorithms are, just our general approach to like coming up with the algorithm first of all. And then I feel like the hard part of divide and conquer algorithms is calculating the running time as well, because like once you have the recurrence, how to like unroll that and get the running time. So Jenny will be going over in detail like how to unroll the recurrence and like kind of solve it for all the general cases. And yeah, we also put up, she also put up a video for that. That was very helpful. So you can always refer back to that and like we'll put up these slides, obviously.
It's the same thing. So like if you didn't get anything, you just go to see the video.
Yeah. Yeah, and then after that we'll go over like an example problem as well. And so there, we can like kind of solve that together, come up with the sort of like recurrence relation and then also go over how to prove it. Yeah, so first of all, just like a general approach for DNC algorithms. So for divide and conquer algorithms, yeah, you want to use a series of recursive calls to like break a problem down into smaller parts and then build up an answer using the answer to those smaller parts. And so I guess yeah, one thing is like how you identify if like like given that you have like a bunch of tools that you could use like greedy or DP or divide and conquer, how can you like guess that you can use divide and conquer? So I feel like yeah, so for problems like Mozart where you feel like a simple like greedy approach won't work, but you don't need to do the memorization that DP requires. I feel like divide and conquer is good for those problems because you are still splitting down into subproblems, but the structure is still like simply recursive. You're not storing any of the answers in memory. You're just, whatever the recursive call was, that's the only thing that's using like the answers to your subproblems. And so that's where a divide and conquer algorithm is like usually useful. Yeah, and then so generally, yeah, these are sort of like the main steps you'll need to fully specify any divide and conquer algorithm, which is like, first of all, you want to come up with a recurrence. So while you're trying to think of that, just kind of like assume that, oh, let's say we kind of know the answer to our question for every smaller piece of the problem. Now, how can I just like focus on building up recurrence? So let's say that you're given like yeah, so try to break the like like if there's an array or something like that, try to break the problem down into two or smaller pieces and then think that okay, if someone would give me the answer to my problem like for these two pieces, how could I like combine that to yeah, get a solution to the overall problem. And yeah, I think yeah, you were asking if there have to be at least two pieces.
Yeah, I think sometimes you can have questions that only have one subproblem. So for example, binary search, if you know like those are like all larger, you can just go to the other side, doesn't matter.
Yeah, so I get, yeah, so there you're sort of like discarding one of the pieces, but I guess I would personally still picture it as like you're dividing it into two subproblems and then you're discarding the answer to one of the subproblems. Yeah, something like that. So like yeah, basically like the subproblem you have, it definitely has to be like smaller size than the array.
Yeah, it doesn't make sense if you're like dividing into two and you're just gonna mess up.
Yeah, it has to end to work. So yeah, and then so yeah, once you have the recurrence, like that's you're thinking about sort of like the big picture, like you can just assume that I have the answer to all of my subproblems. And then after that, you want to make sure that you have a base case. So, let's say you have like a length one array or like, yeah, whatever size of problem such that you can't really split any further, that should be your base case. So yeah, for like Mozart, let's say you have like the size like two problem for example, like yeah, like that. So yeah, like make it like define what you would do in that base case because only then is your algorithm complete. And so, yeah, a classic example would be like the Mozart algorithm. And so there, if you want to sort an array, you're gonna like use like a pivot and you divide the array into like those two parts. And here, that's a recurrence. You're assuming that my recursive call is gonna sort those two arrays. And now my combined step is gonna be that linear time combining of those two pieces, and so I get my sorted array. And then yeah, we also know what the base case is going to be, and yeah, how we're going to deal with that. And so yeah, that's like your fully specified work chart. And then generally the proof for BNC algorithms is going to be induction, and so we just induct in the size of the input of the problem, or like the size of like whatever you're breaking down. So yeah, for the inductive proofs, I recommend like the same structure, like don't overthink it. Just base case should just be my length one array, length two array, whatever you were using as a base case, just proving that your DNC function returns the correct answer for that size. And then for induction, you can kind of use basically like quote unquote strong induction. So you can assume that if you're trying to prove like your correctness for size n, you can prove that you can assume that all of the subproblems for like less than size n are like your function is correct for those, and then yeah, you can basically just prove your induction by explaining your recurrence. So in that case, it's kind of similar to like DP, where like the proof is like once you come up with the recurrence, the proof is just restating and explaining why it makes sense. So for Mozart, let's say that okay, well by induction we can assume that for like the two pieces in our array, like the function returns the correct like sorted value. And now that we can assume that to our inductive hypothesis, if we're merging those in like our linear way, and like yeah, you just show that the way that you're merging those answers in will give you a sorted array for your like final answer. And so that's your inductive steps basically. Yeah, so yeah, just wanted to go over like I guess like one of the examples of like integer multiplication. So yeah, this is I guess this would be like slightly similar to also like the matrix multiplication example that you might have covered in class. But yeah, so this is sort of like a divide and conquer way to be like multiplying two integers. And so yeah, so this is just like if you like divide an integer into like two halves, basically, this is gonna you can use like this formula to compute like the answer. So this is just it's sort of by like the FOIL method. This is just like the formula you would get if you like expand that out, right? And so yeah, and then so yeah, these are your subproblems would be computing the product for like A1 and B1, A0 B1, A1 B0, and A0 B0. So you have basically like 4 subproblems, and you're kind of breaking your integers, each of them down by like a factor of 2. And yeah, so 4 different products, and then when you're adding these numbers, so that's followed by the number of digits, it's of n. And so the total runtime for recurrence becomes like 4 times p of n over 2 plus O of n. And so yeah, the reason so yeah, I guess the reason we're going over this example is just to like kind of show how you can like kind of quickly analyze the runtime of something. And so the n here is just like the length of each integer, and so we want like an efficient integer multiplication algorithm that scales with like the length, so sort of like logarithmic with respect to the actual value of the integer in base 10, I guess. Yeah, so yeah, just to like explain more, the n over 2 is just going to be because we're splitting the integer into parts, and we have 4 of those base cases. 4 of those subproblems, and so that's 4 times p n over 2, and then O of n to do these additions in the formula, which is going to be linear because to add like two integers, since you're adding at each like position of the integer, that's like O of n with respect to how many digits there are. Yeah, and then so in this slide we just see that from this recurrence we can tell that the total runtime is O of n squared. But yeah, we'll cover how to calculate that in like the next slide. So yeah, right now just kind of the important thing is I guess just coming up with this inductive recurrence formula for the running time, and then we'll go over in more detail on like how to calculate that.
Do you remember how they? Oh, you're going to come down to like series of problems.
Yeah. So so if we go back to like this formula basically, so we realized that here we were doing like A0 B1 plus A1 B0, so like the first half of A0 times the second half of B1, and then A1 plus B0, A1 times B0. And so we realized that instead of computing all 4 of these subproblems, we can actually just limit ourselves to computing 3, which can get our running time down. And so, yeah, this slide kind of explains how to do that. And so, yeah, this is just kind of like mathematically pushing things around. So, yeah, you can compute this sum in terms of A0, B0, and A1, B1. And yeah, that's again just sort of, like by file, if you like kind of expand this out, yeah, we'll see that, yeah, this comes out A0, B1 plus A1, B0. And yeah, the reason this works is just like multiplication is more expensive, so we want to minimize how many things we're multiplying, but addition is like, yeah, essentially like easier because it's linear time, like it's O(n), right? And so yeah, that's why, yeah, because we have this formula, yeah, so yeah, so yeah, now our subproblems basically become multiplying A1 and B1, multiplying A0 and B0, and then we do have to compute A0 plus A1 and B0 plus B1, but then we just need to multiply those two together. So that's our third subproblem. So yeah, we have like 3 subproblems that are splitting our original case into like by a factor of 2, because yeah, we're having it, and then our combined step is just going to be doing all of these additions. So like, doing like minus A1 B1 minus A0 B0. It's like that's just combining the results. And yeah, so our new recurrence then becomes like 3 times t to the n over 2. So yeah, the only thing that's changed is just the number of subproblems. And so and yeah, the combining steps are remains linear. And so yeah, again, as now, yeah, in the future when we cover how to like calculate how to like unroll our recurrences, we'll see that our total runtime becomes n to the like log base 2 of 3 as opposed to n squared. So that's a little bit better. Yeah. And so imagine.
Yeah, okay. So I'm going to talk about how do you like generally calculate the runtime for divide and conquer questions. So just to reiterate like the workflow of the general question. So first you divide the original question into like several pieces of subproblems with equal size. So I think equal size here is pretty important because when you're dividing those, they merge sort. You want to divide them into like n over 2 and n over 2 instead of just dividing them into maybe say one subproblem only has one element from the array and the other one has the rest. So it doesn't make sense. And also, we're using the unrolling technique, which I'll go over later. So if you don't have equal sizes of subproblems, it's basically impossible to calculate the runtime using that technique. So just, yeah. So always keep in mind you have to make it equal sizes. And then similar, you solve the subproblem recursively until you hit the base cases. And then after you get all those answers for your subproblems, because we assume they're all correct, so we can combine the results to get the final solution. So one point that I want to point out when calculating the runtime is that you kind of need to consider the time for both the splitting part and combining part. So like the divide step and the conquer step, because sometimes the divide step is not just simply change the pointers to the original array. Sometimes it takes more time. So just when you're calculating the runtime, you have to put all those runtime into consider. And then this is kind of the general form of a the time complexity equation for divide and conquer questions. So basically, you have the t of n over here, which is represents the original problem, and then you got a few numbers of subproblems here, and then also the combined step. I put the O of combine here just like arbitrary like placeholder because it can be different from every question. It really depends on the question. So I don't want to just put in like O of n or n squared something to confuse you guys. So basically, this really depends on your algorithm and it depends on the question. So Q here is the number of subproblems we divide the original problem into, which in the merge sort case we divide them into 2 subproblems. So Q is 2. And then the N over P is basically the size of each subproblem. And then just as we said, normally it's like, well, it's not normally, you should make it like smaller each time instead of like bigger or like just stay the same size. So notice how this form is not like a final runtime, which we normally write in the form of O of something. So actually, it means that we need to solve this equation to get the actual runtime. Okay, So this is something, if you want to memorize, I guess this is kind of a simplified version of what is called the master theorem. So this, okay, so those three equations here only works if the combined time is linear. So if you have like some runtime equations like this, you can use those three complex, like three theorem equations, I guess. But if it is not off, and then you have to calculate it like otherwise. But at first you don't have to memorize this because I'm going to talk about how to calculate those in general. And also, I think there's like a more general version of master theorem. So if you're interested, you can check this link. There's like a formal proof of master theorem. Okay, so go back to master theorem. Um, so the Q here, again, it represents the number of subproblems we have, and then P, and over P is like the size of the subproblems. And if Q is smaller than P, and then your whole algorithm gives O of n runtime. And if Q equals to P, then it is O of n log n. So one of the examples is just a merge float, because we divide the original array into two subarrays, and then each one is size of n over 2. So in this case, both P and Q equals to 2, which gives the runtime of O n log n. And the last case is that Q is larger than P. So this is kind of the example with this in the integer multiplication, where you have each time you split the subproblem into half of the original size, but then you have three subproblems. And then the runtime is going to be n to the log of P of Q, which if you go back and then check the runtime, it matches here. Because one is 2 and the other one is 3.
Yeah, and I feel like it's useful to like at least kind of have these relations in mind, because one case where I found that it helps is, for example, let's say you get an exam question that says, okay, come up with a divide and conquer algorithm that gives you a running time complexity of like O of n log n, for example. And so if you know from this recurrence, you can kind of like actually, yeah, if you know what runtime you're supposed to achieve, you can kind of build up what recurrence formula you need. So if I want O of n log n runtime, it's likely that I'll be splitting into like two subproblems. I'll each by a factor of 2, and then I'll have like a linear combine. And so that can actually help you come up with the algorithm if you can kind of guess what the recurrence relation is.
Yeah, it's very helpful in the prelim, especially because sometimes we'll tell, come up with a log n like time complexity algorithm, and you have to do something like this. Okay, so this is kind of example. I copied the code, or like I take a screenshot from Java hypertext, but hopefully I cited it, so I won't get sued. So if you read the code here, we divide each subproblem into size of n over 2, which gives p equals to 2 here. And then see we recursively call the two subproblems, which gives the q equals 2. And then finally in the conquer step, we take linear time. And then this like kind of builds up to this equation here, and then finally gives the runtime of n log n. Okay, so this is the unrolling method, which is the general method I use because I never remember the master theorem. I don't really like remembering stuff, but yeah. So if you understand this method, you should be able to solve like the runtime question. So I guess the general idea of using the unrolling method is like we have all those levels, and then we are trying to solve those different questions with different sizes. And then at the end of the equation, because we computed all those subproblems, we want to add all of the time complexity up, and then to get the final runtime. So then the first kind of the very important question is that how many levels do you have, right? Because you have to sum up all of them, so you need to know like how many steps you want to sum those up. And so to see the trend here, if we want to calculate the size of subproblems, the first level is just n. And then the second level, so this is the example that you have like 2n over 3 as your subproblems. So like I think it would be helpful if we had more examples other than just splitting into half. So this case I put 2n over 3. And then so the second level, or maybe level 1, you have the size of n times 2 over 3. 2 over 3. And then the next level, you have n times 2 over 3 squared. And then so we can see kind of the pattern here. If you want to calculate the size for an arbitrary level I, you get this formula here, which is n times 2 over 3 to the power of to the i's power. So then because we keep like dividing our subproblems, like problems and subproblems into smaller pieces, eventually we'll hit the base cases, which we only have size 1 questions. Then we to calculate the number of levels we have, we can simply let the C equals to 1, right? Because the K level, and then we want it to have size 1. And then if you solve this equation here, you basically can get K equals to log 3/2 times n. So in a more general case, I guess, if we have A or B as like the subproblem size, then we normally would just get the total of log B over A and levels in total. So I think one of the things I want to like bring up is that notice how this number of levels only relates to the size of subproblems. So say if I do a very bad example, say I only divide the subproblem n. So if I only want to divide the problem with size of n and then into another problem of size of n, then basically this level never ends, right? Because you never get smaller. And it doesn't really matter how many subproblems of size n I put into, because it's never gonna end anyways. And then the same thing here, if I just stuck in more subproblems with size 2n/3 here, it doesn't really matter because they're still gonna break up, and then eventually we will end at level here. So the only thing that matters, like that affects the level of, so to speak, the affects the depth of this tree structure here is the size of the subproblem. Okay, then we want to set up the equation. So basically this tree is constructed from the equation given here. Normally that's like what you have, right? Because you design your algorithm and then now you have this equation and you want to like kind of calculate out the final runtime. So this is the tree structure you have after like you draw this thing out. So from this equation, we have 3 subproblems, which correspond to like the 3 subproblems here. And then also each one is divided into size of 2n/3. So then because okay, so when we're calculating the divide and conquer runtime, one thing I want to say is that you don't really, because we assume you get the answer from the subproblem. So the only runtime for that particular level only comes from the combined step. Because like all other runtimes we'll consider, so you might ask like, what about the runtime for calculating those subproblems? Because we're going to like cover all the subproblems in their own levels instead of like an upper level. So to speak, then the first level, the runtime, because we have a problem with size n, and then so if we plug in this equation, each a combined step, we have n cubed runtime. So this is like the total runtime for this level. And then in the second level, or maybe level 1, we have 3 subproblems. So and then each one it takes 2n/3 cube. Right? So this thing is very important here. So you really want to remember how to do this. Like you don't want to get this thing wrong here. So so if you consider this equation, I found it confusing when you're using n because the n kind of differs for different levels. So instead, I encourage you to think about it as a function. So instead of using n, you can use x actually. So this thing is like exactly the same thing here. But then so in this level, our x is actually 2n/3. So if you plug in x equals to 2n/3 here, you got this equation instead of this one. So the difference is that the factor of 2/3 gets cubed in the correct formula, and it's not cubed in the second formula. And then it doesn't really make sense if you just put a constant factor here without like cube it, because they're like they belongs to each individual subproblems. So it's kind of a little bit subtle here, but you will like if you get more practice, it should make a lot of sense. So just to keep in mind that when you're like calculating the runtime, you want to kind of get a separate variable to make sure you don't like calculate the wrong thing. And then if you follow this trend at the like arbitrary level, I guess you can have this formula is 3 to the k, or we can call it I or something. So it's 3 to the k, and then 2/3 to the k because you want to like make the size smaller each time. So each time you times another 2/3, and also this thing, the whole thing is cubed. Okay. So this is the formula we just get from the tree graph. And then now, just as I said, we want to add up all the runtimes from each level. And then, so basically, we have this huge sum here, which is sum from the level 0 to level k. So basically, we're summing all the runtime from level 0 to level k. And if you do some simplification, it just goes to here, this step. Notice how the n cube here is not like, it won't change because the k is the only thing that is changing here. So you can treat it as a constant and then just get it out. Then the only thing that matters is this sum here, which is if you sum 8/9 to the k's power and then you sum often. So you might ask, like, how am I supposed to calculate this thing? So I got this more general form here, and then you only have to kind of memorize those three cases, but not really, because I will talk about the integration. So if you have a general case like this, it basically only has three cases. Either r is equal to 1 or smaller to 1 or greater than 1. If r is equal to 1, then basically this thing can be expanded as 1 plus 1 plus 1 plus 1, and then you just plus k plus 1 for like k times, right? So it is of k. And if r is smaller than 1, then this thing basically, so this thing is obviously smaller than this thing, because in this equation, we only have k terms add up together, while this thing we have infinite terms add up together. So this thing is definitely smaller than this thing. And then this, if you can recognize it, this is the formula for the geometric theory. And I won't go into the derivation, but you can remember this. This is equal to the 1/1 minus r, which eventually gives you off 1. And I guess the last case is that when r is greater than 1, it follows this formula here. I know it's kind of like weird, how did you get this? But then I put the, like, how you can get this in the left corner, so you can't go through the math. It's not that bad. And then once you like I guess once you see this, you will remember it. And then if you don't want to remember like the derivation, you can just remember this thing. But so if you got the formula here, it's r to the k plus 1 minus 1 over r minus 1. Maybe I should put r like smaller than or equal to r to the k here, because you kind of divided it with another r. And then yeah, in that case, it is bounded by of r to the k. So come back to this formula we had before. This case, r equals to 8/9, which falls into the second case, which can be simplified to O of 1. And then combined with the n cube here, we still have, this gives a total runtime of n cube. So notice how if we don't like cube our 2/3 here, you might fall into the third case, which will give you the wrong runtime. So like you don't really want to do that. So just remind you, like when you're doing this step, you don't like left out the cube here. Yeah, there's another method called substituting method. We won't go into detail of this method because normally it's used to like get a more like tighter bound for those parameters. So for example, instead of just arbitrarily stating the runtime is O of n, we sometimes, it's not O of 4n, it's just 4n. So instead of bounding the runtime to O of n, we can just say, oh, this is at most 4n. So the way you do this is like you guess the final runtime and then plug it back into the recurse to see if the equation works out. So I guess the idea is that if the thing you guessed is true, then it must satisfy the equation you have. It sounds pretty weird, but I mean, it's basically still induction because you assume like everything previously is correct. And I recommend it, if you're interested in this, I recommend you to read more on the textbook. And then we will go over some example problems.
Yeah.
Societies. Oh, nice.
Yeah. Okay. Yeah. So for this example problem, yeah, we're gonna go over the solved exercise 2 for Kleinberg and Dardo's chapter 5. And yeah, so yeah, I'm just gonna give everyone like a minute to read this, but I'll also like explain the problem. So yeah, it's just a lot of words. Yeah. So yeah, but the gist is that let's say you're given the stock prices for one stock for n consecutive days, and you want to find a strategy. So you just want to buy that stock on one day and you want to sell it on another day, and you want to find what the best day is to buy the stock and then to sell it to make the most money. And so the example that they give here is like, for example, let's say you have stock prices for 3 days, and so the price on day one is 9, the price on day two is 1, and then the price on day three is 5. And so here, the best thing you could do is to buy the stock on day one and then to sell it on day three, so that you get a profit of 4, right? Because it's just like, yeah, you sold it for 5, bought it for 1. Um, yeah, and so yeah, and obviously the constraints are that you need to buy it before you sell it. So there's no like, I don't know a lot about stocks, but yeah, in this problem that is not possible. You can't like sell some. You can't.
don't
Yeah.
sell stock from yesterday. Like
Yeah.
you don't buy it tomorrow and then sell it yesterday anyways.
Yeah. So yeah, and yeah. So the question says that there is like a simple algorithm for this that would just take time O of n squared. So you could brute force it by literally just trying all possible pairs, of buy selling days and then seeing what makes the most money. And so, but what the question is asking you to do is to do something a bit better, and then trying to find the numbers I and j, so the buy and sell strategy, in time O of n log n. So yeah, just gonna give people like 5 minutes to like look at the question and maybe like think about things, and then we'll kind of go over and like discuss them.
Also, if anyone has any question about like what we just said before, like general like runtime or maybe other stuff, feel free to
Oh
type in
yeah,
the
yeah,
chat.
definitely.
I can't really see chat.
Yeah, I can monitor it on the.
11 one. Choose. Also, I guess general suggestions like for all the chapter, I strongly recommend to go through all the soft exercises. They're very helpful. Just in general.
Okay. Yeah. So yeah, now that maybe everyone's had enough time to like look at the question, yeah, one thing I like you notice here is that in this question they were nice and they were like, okay, we want you to give us an n log n algorithm, and so that gives you a little bit of hint of, like if you do something with that recurrence piece, you will achieve that n log n bound. And so as we've seen before, so for, like classic cases, Mozart, you split your problem into 2 subproblems, and each subproblem is of size like n over 2. And then your combining step is O of n, so linear. And if you do something with that structure, then you can achieve O of n log n complexity. And so yeah, so 2 subproblems of size n over 2 with linear combined time. And so yeah, maybe let's try to think of just like the most intuitive way to split this into 2 subproblems, because yeah, we want them to be like non-overlapping, right? So let's just say so the answer that in this case that we want is like those two indices, basically the index to buy and the index to sell in the best case. And so yeah, let our subproblems just be like, if we just consider days from 0 to n over 2, and then the days from like n over 2 plus 1 to n, basically, like, we just split the price array into like half, and then we just consider, okay, the best buy sell strategy if we're only looking at the first half of prices, and the best buy sell strategy if we're only looking at the second half of prices. So, if we have that sort of setup, and yeah, so yeah, that would be your subproblem. And so yeah, now when we're trying to come up with the recurrence, like, what we want to do with this, yeah, the best thing is to just like, yeah, okay, assume that you have the answers for both of these subproblems. How would you be able to like combine this to get an answer from like, yeah, your final like, n month array? Yeah, I know it's on Zoom, so I guess like less interactive, but if people have any ideas, like feel free to speak up. I feel like this helps you like, um, yeah, like think of like potential answers and stuff. So you can also feel free to type in like the chat if you're yeah.
For me, just some like thoughts about this question in general.
Yeah, because like the way that I like usually find it helpful is to just like, try to divide this into like, again, like kind of like DP, just like all the possible cases that could be happening in this problem. So, if we have the answers to our two subproblems, then one case, so our two easy cases just become that, okay, we are buying and selling both in the first half, or we're buying and selling both in the second half. So like, let's say that actually is the optimal answer, in which case we can just kind of use the answers from our subproblems. But then the tricky case is that, okay, let's say, yeah, what if the best time to buy falls between days 0 to n over 2, but then the best time to sell falls between like the second half, essentially. Yeah. I think you have to like, yeah. Yeah, I feel like we should get the room changed maybe, because it's like Geo1 is the blackboard. Yeah, it's easier to like draw. Yeah. Oh, yeah. Okay. Yeah. So the cases that we wanted to consider is basically, the first case was like your best solution is to buy it sometime in the first half and then also sell it sometime in the first half. And second case, like same parallel case for the second half. And then the third case is our interesting case where we want to buy in the first half but sell in the second half. So we can kind of see that the first two cases we just get with our subproblem. So that's, when we make the recursive call, that we'll get the answer to that, right? And so now how do we like combine the information that we have to, first of all, like calculate some answer for the third case, and then like get the best answer for all three cases? So the way that you would get the best answer would just be, to like get the maximum of like the three cases, like, either you're doing the first thing or the second thing or the third thing, whatever gives you the most profit is the best case. And so, yeah, like any ideas on how we can like calculate our answer for the third case, where we're enforcing that you have to buy it sometime between 1 to n over 2 and sell between, like the second half, like so n over 2 plus 1 to n, basically. And so this will kind of come in our combining step, because we're not making this a sub problem, because it kind of overlaps. It involves both halves, right? So and we know that based on our complexity analysis, we would like it to be linear. So basically, just like a linear way to do this calculation. Any suggestions? Feel free to type in the chat as well. No. Yeah. Okay. Yeah. So yeah, we can just go over, how you would do this calculation. And so yeah, we know that the our constraint is like it has to be linear time, and yeah, you wanna buy it sometime in the first half, sell it sometime in the second half. And if we have that constraint, then so we know that the profit is just going to be the price at which we sell and then minus the price at which we buy, right? And so in these cases, the best thing to do is to just get like buy at the lowest price in the first half and then just sell at the highest price in the second half. So all we need is like the minimum of the price in the first half and then the maximum of the price in the second half. And that's how we get around to the third case, right? And we can see how that's like linear because it's just min and max. And so yeah. So yeah. So yeah, for our combining step in this problem, basically the first thing we'll be doing is like calculating case three. So that takes linear time. And then the final thing we need to do to combine is to just consider all the three cases. And so that will just be, kind of constant time. We're just comparing what of the cases is better. And so our time complexity for the combining step will be linear. And then
Oh, can I add something? So I guess just as a follow-up to this question, sometimes you can make those subproblems to return more information. So if you really want to make a runtime even better,
Oh.
you can achieve all of N10
Okay.
for this question. Do you want to talk about that?
Yeah,
Are we
and yeah, I was gonna do that as like a discussion
Oh,
thing, so I just kind of lost slide that was like, do we do better?
Okay, cool. I guess the answer is we can
yeah.
do better. But then yeah,
Yeah.
so I guess there's you can try to let those subproblems return more information than just some naive, okay, maybe I and J. So like you can definitely define your algorithm to do more than that.
Yeah. So yeah, before that, we can just see that, okay, we've come up with like a recurrence and the combining step, and now, as always, we also have to think about what the base case should be. And so yeah, like logically, you just think about, okay, when would it not make sense to have a subproblem? And that's just like, okay, if you have one day, you can't really do anything with that, right? So our base case should be if we just have pricing for 2 days, then yeah, you have to buy on day one and then just like sell on day two. And so
Maybe not, right? Because if day one is higher than day two, just do that.
if day one is
You
a
don't
high,
want,
yeah.
I guess something like this, but you got the idea. It's like
Yeah, like basically if you're getting negative profit, then you should
Just
return
return
like
zero.
yeah, you should have like a special kind of case that where your function returns that, oh, in this case it's better to like do nothing. And so yeah, in which case like yeah, your profit is just basically zero. So when you're getting like the maximum of case one, two, and three for your subproblems, like if one of them is zero, then yeah, because you're just getting the maximum that will like consider that case. Yeah, and so yeah, that'll be our base case. And yeah, so one like last kind of detail that we have to think about is um like yeah, since our base case is of size two, uh yeah, it's a bit weird to see if like n is not a power of two, like how we're gonna do the splits, because you might end up with like a base case of like size one or three or like some weird odd number like that. And so the way that in the book they get around this is like you can just make n a power of two by just extending the array where the price on like all the future days is just the same as the price on like the last day. So functionally, that's not going to affect your answer because like then if you could sell on like day n, then you can sell on like yeah, whatever you're augmenting the array with, like it's just the same price. Um yeah, and that just makes sure that when you're doing the splits in half, you're always getting a clean split, and your base case is always nice too. But yeah, I think you could also like yeah, like when you're doing the splits, like try to come up.
You just define several base cases. I don't know.
Yeah, it just yeah,
don't know.
it would just become like a little less clean because then you'd have to consider like, oh, it's three, or yeah, like if it's an odd number, split basically. In which case,
I guess it depends on the question. I guess this one it might be fine. But
Mhm.
then the way
Yeah.
if it is not like power of two or like power of the size of your subproblem, you might want to like do a little bit about the original problem.
Yeah, yeah, and like like usually I feel like if it's like more torn or something like that, it's like the base case ends up being like size one, so you don't have to worry about this. But yeah, do think about like, oh, if your base case is just size two, then you're always gonna end up with something size two and not something weird. Yeah, that's important to think about. And then yeah, just for the proof, yeah, as we kind of went over before, we'll just use like strong induction on n. So like the best strategy, uh, on from days one. Yeah, actually, yeah, for this, usually, I guess what you should induct on is like, um, let k be like some subset of k days from the n prices. So your inductive assumption is like, okay, let's say for all k less than n, we're assuming that we know the answer, uh, for yeah, like the for any window of like k days, out of the n prices, we know our answer, and then we'll use that information to like build out our answer, to like the n level problem. And yeah, the base case for the induction is again just like what we explained for like the 2 days. And yeah, so yeah, usually like for this, yeah, I was gonna like do like an overleaf write up maybe, and then just like upload the PDF as sort of like a model proof that you can use as like a reference. But yeah, and this is also like a solved problem in the book, so you can also see the way that they come up with a solution. Yeah, and then yeah, as Jenny pointed out, can we do better? Yeah. So what we saw here is, so yeah, here the PNT question, it was asking us to do n log n. So we just did what they were asking us to do, and we didn't think about like optimizing further. But yeah, what we can think about here is, yeah, so our combining step, it seems a little bit inefficient, because when we're calculating case three, we realize that we're taking linear time, and like let's think about whether we can do better, right? So what we're doing for our case three is like we're getting the minimum price from um the half 1/n, from the first half, and then the maximum price from the second half. Uh, and this also has a very nice like divide and conquer structure actually. So what you can think of is, okay, what if these min and max values for each half of the array, we actually have our subproblems return that as well. So what if our subproblems, first of all, return like the best index to buy and sell, of course, because we need that, but then it also returned the minimum value for that array and the maximum value for that array. So if we have that information, we can calculate case three in constant time as well, and then do the combining of like finding the best case in O1 time as well. So that changes like our inductive formula structure basically, and we'll get a better runtime from n log n. So we'll end up just getting O of n. And yeah, for the sort of like the min max subproblem, yeah, the way that you can do the combining there is like, so okay, let's say we have the min and the max for each of our two halves. The way that you get your new min is just getting the minimum of the two minimums, and then the max of the two maxes, right? And then so you can return that information up to like any bigger problems that are being asked for your recursive call. And yeah, of course, like for your final answer, you just need
The
sort of,
INJ,
yeah, you just the I and J, and so you can kind of at the end you can discard all this min max information, but yeah, it's helpful to have your subproblems return that, because that helps you get the runtime down. So yeah, as Jenny said, like also this is like a useful thing to consider. Like if you feel like you're not able to get like a good time complexity by just having your subproblems be like exactly what the question is asking for, then always think of like augmenting what the question is asking for with like a little extra information, and that can help you like reduce the complexity of the combining step. But yeah, I always feel like starting off with like just what the question is asking for is like a nice way to at least like build up like the recurrent structure, and then you can always think of optimizing it.
Yeah, and then sometimes when I'm doing those questions myself, I'll write down like what all those things like means. Like for example, I'll write down the first sub problem means like the I and J in the first half that gives like the maximum profit, and then I'll write down the second one is like I and J gives the maximum profit for the second half, and then I'll see, oh, how like are there more cases there, and then how can I use those results from like previous questions that I know is correct to build upon this question. I feel like sometimes it's helpful to write it out, but like it depends on the question, I guess.
Yeah, definitely. And like, yeah, when you're coming up with the recurrence, it's try to just kind of like forget that you have to solve the sub problem.
Yeah,
Like, you
just
know, just
assume
forget
it's
that
correct. Yeah.
because it just become like, you don't try to get like lost in that. Just assume that, okay, let's assume we just know the answers to everything and how we can combine it. Because then I feel like it becomes a very like logical, straightforward process. Yeah, so any questions on like the sample question or like, I don't know, any general questions about divided conquer algorithms over that? Great. Okay, yeah, so if there's like no questions, then so we'll post the slides on Ed, we'll post the recording on Ed, and I will also post like a small like kind of PDF write-up of the like kind of the proof answer or like, you know, the way that you'd be expected to like write it out. And so you can always use that for like homework solutions, exam structure, like things like that. Uh, yeah, and yeah, that should be it for this recitation.
Yeah,
Once
and
again,
also have office hour at 2 today. So if you want to say hi. Yeah, or like further question about the runtime stuff, whatever. Yeah.
Mhm. Yeah, and then of course, like Jenny also uploaded like a separate like video about the running time calculation.
Yeah, it's like basically the same thing, but then I was like, when I was explaining, I was trying to write about it, so hopefully it'll be like more clear than me just talking about through the slides.
Mhm.
Yeah. And that should be it for today. Thank you guys for coming.
Yeah, thanks for coming. I know the weather was bad, so it makes sense that everyone was on Zoom. Bye. Bye.